Okay, the recording looks like it's going, so fingers crossed. And my stylus has been fixed, at least in the sense that the screen and the stylus now seem to be matching up correctly as they should. And I've even got a little hack, little solution to not being able to find where the eraser button is on my stylus. I just put this little piece of rubber around it, tied it with a string. It's pretty low tech, but it puts my finger right on the eraser button. So I think we're good. Okay, so here's what we were talking about last time. We developed Green's theorem, and the idea was step one to realize that this right here, right, circulation. So keep in mind this is a vector line integral, but specifically a vector line integral around a boundary. Right? When you have a vector line integral around a boundary, that measures the extent to which the fluid is flowing along the curve, but the curve is going around in a circle. So it's measuring the extent to which the fluid is going around in a circle. It's measuring the extent to which the fluid has a rotational aspect to it, like a whirlpool or a tornado or something like hurricane, that kind of thing. Okay, so circulation, we found last time, is an accumulating quantity. Right? The whole is the sum of the parts, chop it up, add it up, just like you do with mass. Right? Just like you do with any other accumulating quantity. It's like circulation is a stuff. It's like it's physical. I mean, it isn't, but it's like it is, right? It behaves as if it is. And so, frankly, it is a good idea, a healthy exercise, to just kind of go around thinking of it as if it's a kind of a stuff, because that's how it behaves, and it's a perfect, wonderful metaphor for thinking about these things. Then we multiply and divide by the same thing, perfectly legal, thus giving us two benefits. One, I thought I had that little eraser button. I did. There we go. Two things. First of all, that turns this into a density. We've got stuff per unit size right there. That's what density is. And again, sweeping details under the rug, this is the formula for how to compute that particular density. The other thing it does for us is it turns this into a Riemann sum, and thus this expression into a double integral. So that's the sort of the broad strokes of developing Green's theorem that we see right here. And then down here I have some alternative notations for it. Nothing really different in any of these versions, but again, some people like this coordinate notation, which again has its merits. And so you may see Green's theorem written like this. This is how I first saw it when I was, y'all's age. But I personally, I like this abbreviation for Green's operator, and there are other different abbreviations. Some people call it curl. Y'all have heard that term, curl. We haven't really done much of anything with it yet, but we will. But for reasons that I'll explain when we get a little further along, I personally prefer not to call it curl, but some people do. So anyway, the big picture to keep in mind, though, is that what we have here is an accumulation thought of as an integral of a density, just like with mass, and so that's the big idea. All right, we did a couple of examples. I won't repeat those, but examples of how in various different places, and of course you do have to keep in mind orientations, right, but in various different places, you'll find that line integrals turning into double integrals can be really useful, because while this, let's see, where's that button? There we go. While this line integral is, it's got three different legs, and I'd have to plug into the vector field, and it's a whole thing, right? On the other hand, this is a double integral of a constant over what I like to call barnyard variety geometric shape, namely a triangle, and it's a snap to compute. Okay, and that kind of thing happens fairly often. Okay, there's a nice little corollary I want to talk about. Very clever idea. Now you'll notice I'm going to start here with Green's theorem. There it is. Just straight up Green's theorem. And what we're going to do is we're going to apply Green's theorem to this particular special vector field, very carefully selected. right? So now, of course, Green's theorem applies to lots of vector fields, but I want to pick this one. When you do, that gives you the alternative notation of rewriting your line integral like so, right, which you could do. Some people like that. You don't have to. And of course, now I can also take this vector field and plug it in right there for f, and therefore I can compute Green's operator, etc. And Green's operator ends up being exactly 1. And oh my gosh, what happens when you take the double integral of 1? Well, you get exactly the area. And so the nice little punchline is that in this case, this single coordinate line integral around the boundary of a shape will compute the area enclosed. And that's kind of wild, right? Pretty neat, pretty unexpected. Now, you may think to yourself, you know what, thanks but no thanks, I'd rather just compute the area, I know geometry after all, and this line integral, come on, it's annoying, right? But there are certainly some situations where this is highly beneficial, and in particular, here's a nice corollary. Wrong word. Here's a related theorem that we're going to use. This line integral, if you compute that line integral over a line segment, a straight line segment, then it is super easy to compute by this handy-dandy little, four-function arithmetic little formula. All you have to do is take your starting point and your ending point, look at the average value of x. Oh, I missed. Yeah, no, that is it. There's the average of the x coordinates. And then you multiply by the change in the y coordinates, ending minus starting. There's your formula to compute this line integral. And so, anyway, nice little fact. Now, I do think this is a nice exercise. I want everybody to take a whack at proving this on your own. It's no big deal. All you have to do is literally parameterize the straight line from this point to this point, and that's a chapter 12 thing. And of course, if you get stuck on any point in this little exercise, you're very welcome and encouraged to come to office hours. Of course, you have my office hours. Don't forget about the TA office hours. By the way, Michael's office hours this week will be changing, and I'm going to be emailing y'all about that early this afternoon. But anyway, you've got plenty of resources, so come get help if you need it. But if you just parameterize this line and plug and chug directly, pull back through the parameterization and compute this line integral, you will find, you have to move some algebra around, but you will find that sure enough you get exactly that. Okay, so give that a shot. But here's how we can use it. And I'm going to consider here this region that I have drawn here. Now, yeah, I know you know geometry, but that's a pretty weird shape, and not every angle is a right angle. And it's not immediately obvious and clear how you would compute this area. I mean, I guess you could break it up into 3 triangles, but again, these are not all right triangles, and it could be non-trivial to compute this area directly. And of course, I could certainly manufacture even weirder polygons to apply this example to. Okay, but this corollary of Green's theorem says area is boundary line integral of x dy. And this boundary is made up of edges that look like that. And if I just add up over all of the edges, if I add up over all of those edges and compute this integral x dy on each one, for each of which it's just 4-function arithmetic, then bam, out comes my answer. So here is that arithmetic. Now let's just kind of walk through a couple of those. Well, we'll look at the first piece anyway. Looking at this first edge, want to compute on that edge. I want to compute integral x dy. Remember, that's the average value of x times the change in y. Okay, what is the average value of x? Well, I've got a 1 and a 2, and the average of those two values of x is 3/2. Everybody good? All right, now let's see. The second factor is change in y. Well, y changes from 1 to 2, or said differently, goes from 1. What did I just say? It goes from 1 to 2, so the change in y is 2 minus 1, which is just 1. So look how easy that was. That was super easy. So you can just proceed with, the next edge looks like that, and then the let's see here, colors. The next edge is going to look like that, and just proceed all the way around. A little bit of arithmetic, and boom, here's your answer. Much easier than trying to remember Heron's formula for the area of a triangle and all that business. Okay, everybody happy? Okay, cool idea. Okay, so here's a wonderful little argument, very, very clever. This is the first, by the way, of at least 3, I think it is, analogous arguments that I'm going to be showing you over the next, week or so. We saw the fundamental theorem of line integrals, and it's a statement about curves and their boundary points. We saw Green's theorem, which is a statement about areas and their boundary curves. They seem disconnected. One is Green's theorem is a 2-dimensional theorem. There's unavoidably a 2-dimensional region there, right? Fundamental theorem of line integrals is naturally, fundamentally a 1-dimensional result. There is a curve, a 1-dimensional curve, and it's boundary points, etc. So the clever idea is to notice that this diagram right here can be thought of as relating to either of those scenarios. So, for example, notice I can think of this picture as involving one curve and another curve that share the same boundary. In other words, they start at the same point, they end at the same point. Now, that's just one interpretation that you can take of this picture. Right? On the other hand, you can also think of this picture as being about a 2-dimensional region, and it's whoopsie, I wanted the color there we go, and its boundary like so. And its boundary, of course, you can just look at the picture there and see the boundary of D, following the rule, region on the left, includes moving along the path C1 in the direction C1 is going, but then it also requires going along C2 but backwards, thus the minus sign. Yep.
What do you mean, like region on your left? Like, what does that mean?
Yeah. So as you are moving in the correct direction along a boundary, as you're going, that's your left.
Got it. Okay.
And that's your right.
Okay.
Yeah. And so you need to make sure that as you look to your left, you're looking into the region itself. Yeah. It's a great question. Anybody else? Everybody happy with that? Make sure everybody's comfortable. Okay. All right. So, 2 different points of view. And I'm going to capitalize on that as follows. Let's see here. First of all, I'm going to write down Green's theorem. Green's theorem says that if you have a double integral over the region, there's my region, D. Right, double integral over the region, then I can view that as a line integral around the boundary. Now again, pay attention to the operators. The line integral is of a vector field F. The double integral has an integrand that is Green's operator of F. Okay, nevertheless, this is just Green's theorem right here. Is everybody okay? And with this particular setup, some really good stuff happens, and I'm going to move out so I can keep this all on the same page. Hypothetically, let's just ask the question, what would happen if Green's operator were 0? Well, let's just think it through. And by 0, I don't mean 0 at one point. I mean it is flat 0 everywhere. Okay. Well, if it's 0 everywhere, then that means that this double integral is 0. No matter what region D you're looking at. That's 0. Well, that means that this right-hand side has to be 0 also. That's right, because it's an equation. And, well, wait a second. If the right-hand side is always 0, that means that these two individual integrals here, I mean, their difference is 0. That means that these two individual integrals are the same for any region D. And therefore, what that means is these two line integrals are equal for any two curves, C1 and C2. And that means that my vector field is path independent. And that means, recalling from a few days ago, that means that our vector field is a gradient. So what we have here, this is one of my favorite little arguments in the course. We have a geometric motivation for why it is that when Green's operator is 0, you're looking at a gradient of something. One of the lifetime theorems that I talked about a while ago. One of the exactness of that mysterious sequence that I put together, seemingly arbitrarily, right? So this is a powerful motivation for why those operators should be put together in that order. It's because they fit together very naturally in this picture. Is everybody happy with that? It's very cool. And not to get too far ahead of things, but FYI, this argument, again, this is version 1 of this argument. We're going to see at least two other highly analogous arguments where we're going to do equally clever, almost rip-offs, just shameless copycat rip-offs of this argument, but applied to different geometric circumstances that are going to arise pretty naturally. So it's an important argument to understand because, again, it's foreshadowing more such arguments. Hey, let's take it the other way. What happens if your vector field is a gradient? Well, if your vector field's a gradient, we know that means it's path independent. If it's path independent, we know these two line integrals are equal. If the line integrals are equal, their difference is 0. If their difference is 0, then the right-hand side is 0, and this being an equation, that means that the left-hand side is 0. Now, wait a second, how could that be? How can we have an integral here that's always 0, no matter what domain you pick? Every domain, the integral of this thing here must be 0. What integrands can you think of for which the integral is always 0, no matter what region you integrate over? And I claim that there's really only one possibility, and that is that integrand itself must be 0. And again, assuming regularity, continuity, etc. And again, I don't want to get bogged down in that kind of stuff. Yeah, how about that? I think that's another lovely argument. Okay, all right, so good stuff. Moving along, I want to talk about an idea called flux. Let's see here, come on, there we go. Flux is a really interesting concept. It's ultimately just a formula, but it does have a really important physical interpretation. Now, I'm going to start with the two-dimensional version of flux. So we're going to imagine a two-dimensional scenario here. So this is we've got a vector field. I want to interpret this vector field as representing the flow of a fluid. So you've got to visualize a two-dimensional fluid. Now, pick your favorite two-dimensional fluid. If you want to think about it as surface water flowing along the surface of the earth, that's cool. If you want to think about it as somehow I find it appealing to imagine a herd of some sort of pack animal. I don't know. I keep going back to wildebeests, but it's kind of a fluid in a way. And even when you watch them move, with these aerial photographs they can take, it's very fluid-like. Right? So anyway, two-dimensional fluid. Pick your favorite. Doesn't matter. And I want to ask the question, just as a general question, if I have a piece of curve, and given that my fluid is flowing along like so, for example, how much fluid is passing through my curve per unit time? a pretty natural thing to want to ask. Maybe this is a part of a border. I don't know, of a national border, or a border of some sort of a park, wildlife preserve, whatever. So it's a pretty reasonable question. You want to know how many wildebeest per unit time are walking into or out of your national park. Yeah. Okay. So a couple of things I want to say about this. First thing I'll say is we're not going to worry about units. That's somebody else's problem. That's details, right? I want to stick to the math, right? And the first thing I'm going to observe along those lines is this component here, the component that's parallel to the curve in question. Who cares? Doesn't matter, right? If there are wildebeests that are going like this, right parallel to my curve, they're not passing through. They're passing by. That's not what we're interested in, right? So how fast they're moving in that direction is completely irrelevant. We're going to totally ignore it. By which I mean, we're going to focus on the other component. That's the component perpendicular to the curve. The component in the direction perpendicular to the curve there. Right? So this component is the relevant speed and the actual direction that they're going, and how fast they might be moving parallel. Who cares? Doesn't matter. Not at all. Okay. All right. So all together then, and now again, you got to worry about units, and again, I don't want to get bogged down in that, but I'm going to make what I think is a pretty simple case that if you want to compute how many wildebeest per unit time are passing across this piece of curve, this calculation does it. Namely, I want to know how fast are they moving in the direction perpendicular to the curve, and then how long is that piece of curve. If they're running faster perpendicular, you're going to get more wildebeest per unit time. Right? If your curve is bigger, well then of course there's, proportionally speaking, more wildebeest crossing across that bigger piece of curve. So I think that's fairly plausible. Hope that is okay. Everybody all right? Okay. And there are some other issues to be considered, but again, I don't want to get bogged down. Now of course, then let me remind you further that a component can be computed with a dot product, at least in the case where that's a unit vector. So very importantly, this does need to be not just any old random normal vector to the curve. It does need to be the unit vector in question, so that this dot product computes that component. Is that cool? Everybody happy? All right. Okay. So, cool. Now, here's going to be a weird little calculation that's we're not going to see why we care about this for a few minutes, and bear with me on this. But we just got through writing down a formula that involves f dot n, and here's f and n, and I'll point out that f, for example, has certain coordinates. We'll call it p comma q, and the n is, let's see here, I'll do this in blue, I guess. The n is, pointing, let's say like that. Okay. That said, I'm going to take everything that I have in this picture now, and I'm going to just rotate 90 degrees counterclockwise. Why will reveal itself later. But for the moment, humor me. I want to take everything in this picture and rotate 90 degrees counterclockwise. Now, in so doing, what happens to a normal vector that's perpendicular to the curve? Well, it turns into the tangent vector, the unit tangent vector parallel to the curve, aka our old friend t. That's just an observation, right? And now, likewise, when you rotate the p P comma Q, well, you're going to get some other thing, and an easy little exercise to persuade yourself, and let me get rid of my distraction colors here. When you rotate P comma Q, the result is negative Q comma P. And easy pitch on why that's true, notice that this dot product is 0. That means that right away shows that these two vectors are perpendicular, and then you can also notice that they have the same magnitude, right? So if they have the same magnitude and one's perpendicular to the other, then one's a 90-degree rotation of the other. You buy it? Okay. All right. Okay, so having done that, look, I had two vectors, and I computed their dot product here, but then all I did to them is to rotate both of them the same amount. And, well, when you rotate, you don't change the magnitudes. You don't change the angle between them. Dot product can be thought of as magnitude times cosine of the angle between them. If none of that changes, then the dot product doesn't change. And that means that this dot product, the dark blue dot product, is the same as the purple dot product. Is that cool? All right, now again, why in the world would we want to do what a weird thing to observe? Fair. We'll come back to that, you'll see. So now I want to consider a more general question of, let's suppose I have a two-dimensional region and I want to compute a flux, but specifically not just the flux through a little piece of this boundary curve. I want to compute the total. I want to add up all the little pieces of flux that I get by going all the way around the entire boundary, right? So, okay, well, we already know from the previous page, let me just come back up here for a quick second, we already know that a little piece of flux over a little piece of curve ds is f dot in ds. So, write that down first. On, for example, a little piece of curve like that, f dot in ds. Right, now I'm going to add up over the entire boundary. Right, so I get that expression, which is not really much of an answer because, after all, I haven't yet figured out how to... Oh, no, not again. Oh, come on. Okay, well, now just real quick, let me just check what my battery life is. It says I'm down to 12%. Okay, well, that's a shame. I'm going to have to get him to get me a better stylus. I need more than 30 minutes worth of stylus. Okay, so this stylus is going to die in about 5 minutes probably, at which point I will plug it back in to charge it again, and then I'll use my finger. Okay. Which is actually surprisingly acceptable. But anyway. Okay, so total flux. So this expression right here, I can write it down, but we don't yet know how to compute this, really. Right? I've seen integrals that have a ds at the end, but not that have a dot product in the middle, and importantly, part of the dot product is the normal vector that depends on the direction that the curve is going at a given... This is a weird calculation that we basically don't know how to do. And this is why this business on the previous page is awesome, is because we showed on that previous page that this dot product is equal to that dot product. That allows me to turn this integral into that integral, and this integral I understand. This integral we've seen before. TDS is dx. And we're experts at computing integrals, vector line integrals of vector fields dx. We've got various different tools. We can pull back through a parameterization. We can try to use Green's theorem. We can try to use the fundamental theorem of line integrals. We got options. Is everybody good with that? So it's a really clever little observation, and in doing so, now you got to be careful with this, but I'm going to write down Green's theorem. Wow, with the warnings. Man, dial it back, man. Okay. So now this looks wrong the way I've written this, but let me expand and remind y'all that when you compute Green's operator of a vector field PQ, then it's dq dx minus dp dy. Fine. But wait a minute, we're not applying our vector field to, we're not applying Green's operator to PQ. We're applying our vector field, we're applying Green's operator to this vector field right here, where, let's see, the Q, the thing that is the second coordinate whose x partial I should be taking is P. Right? And then, minus dp dy. Okay, well, minus first component's partial with respect to y. Well, that first component is minus q. Right? And so that's why this calculation goes like that. Does that make sense to everybody? Just, technically kind of a confusion of variables situation here. But anyway. That being noted, there is what Green's operator looks like, and of course I can rewrite that as this, and this is another theorem. This goes by different names. One way you can think of this, of course, is as a kind of a special case of Green's theorem. This is taking Green's theorem and kind of turning it 90 degrees sideways. I mean, that was the thing that made this all work, is that we related normal vectors to tangent vectors by a 90-degree rotation. That's kind of the connection. The other name that this goes by is the two-dimensional divergence theorem. And we're going to see the three-dimensional divergence theorem pretty soon. Probably tomorrow. We'll start with the three-dimensional divergence theorem. And this is just a two-dimensional version of it. Along those lines, this theorem, now I've presented it as a special case of Green's theorem, but it can also be thought of as its own accumulation theorem. So in the same way that we made an accumulation argument about circulation, you can also make an accumulation argument about flux, outward-oriented boundary flux, is the object in question here. And so anyway, it turns out that's an accumulating quantity as well, and we'll see that argument a little bit later. Okay. Alrighty, moving along. So here, now we've got two-dimensional flux. Understood? Let's talk about three-dimensional flux. We live in a three-dimensional world. Seems like a natural thing to talk about. Okay, so quick reminder, and there goes the stylus. Quick reminder, vector line integrals. Right, so we've talked a lot about vector line integrals, proved a couple of theorems about vector line integrals, but where did it all come from? What were we deep down fundamentally thinking about? We were thinking about work. That was our very first exam. That's the only reason we wrote down vector line integrals in the first place. And then, subsequently, we kind of reverse engineered a connection to fluid flows that was vaguely satisfying. Okay, fair. But the motivation, the foot in the door, work. And specifically, that means that you have to view the vector field as representing forces. So now, as we now proceed to trying to understand vector surface integrals, that's going to be our new sort of topic for today. Vector surface integrals. And it's tempting to think, okay, well, this is going to be a sort of a two-dimensional version of, probably something along the same lines of what we did with vector line integrals. And sadly, it's just not true. The motivating example is got nothing to do with work, and our vector field is not going to be a force. It's just not. So I know that the word vector surface integral and the words vector line integral, they seem to have so much in common, and we've seen so many analogies between different kinds of integrals and the different kinds of things that they can do. In this case, again, the motivating example, totally different. So we're going to be interested in this idea called flux that we've already kind of introduced to a two-dimensional version of it. And in order to understand it, we're going to need our vector field to represent a fluid flow. So let go of forces. There's no forces in this discussion to follow. It's all fluids. Is that cool? Is everybody happy? Okay. All right, now I got to figure out where the eraser... Okay, there's the eraser button. And okay, now I can erase my junk. Okay. Right. Okay. So yeah, here's an analogous picture. Now, previously we were talking about a two-dimensional fluid, a bunch of wildebeests moving across, some sort of a wildlife preserve boundary line or something. Here, three-dimensional fluid. Think, for example, air in this room. And it doesn't flow through curves. It flows through a surface. If I have, for example, let's suppose I have a picture frame, and it's hollow, right? If there's obviously air can't flow through it if there's a sheet of glass there. So it's just the wood part of the frame. But if I were to blow, or if I just observe that, look, the wind and the air in this room is already moving. I can hear the AC. It's on, right? If I hold this up, I could reasonably ask how much air is flowing through where the glass would have been, but isn't, because, of course, that's how air works. Okay, so reasonable question, and here's the answer. The idea is, again, that if you have a vector field representing your velocity of your fluid, then all I really care about is the part that is perpendicular to the surface in question. I mean, the extent to which the air is blowing parallel to the surface, who cares? If it's going parallel, it's going by the surface. It's not going through the surface. We're only interested in how much is going through, and so we don't care about that stuff right there. Yeah? Everybody happy? So again, the component is going to be one of the major... the component is going to be one of the major factors there. And the other factor is, I think it's pretty plausible to argue, is just the area. If there's more area, then there's going to be more fluid flowing through that more area. Seems reasonable. Everybody okay? Okay, so notice then, it's kind of nice that this formula for flux looks an awful lot like our previous formula for flux. It's the relevant component of the vector field, the normal component of the vector field, times the size, in this case area, previously length, right? But the size of the whatever it is that I'm computing the flux through. Okay, so that gives us, in general then, that formula right there for flux. You probably noticed already I'm using this it's pretty standard notation here, capital phi. Same letter of the alphabet, of the Greek alphabet, as the spherical coordinate angle, right? But this is in capital to distinguish it from that spherical coordinate, phi for flux. Right. Okay. Cool. Guess I can just leave that mess. So, okay, but what if we have a surface that's all curved and bumpy and wiggly? And what if our vector field isn't constant? Okay, well, so weird things happen if everything's changing, nothing's constant, everything's weird. Then our argument over here goes to pieces. Here we were assuming that we had a flat surface because we talk about the normal vector, like there's only one because it's flat, right? And we talk about the vector as if there's only one direction and one velocity. It's just all the fluids doing exactly the same thing. Well, again, in the real world, that's not how it works. So what do we do when we have some computation that we're doing, and we know how to do it in idealized circumstances, but we don't know how to do it in general? We chop it up into little pieces, and then we add up over all the pieces. So it's the same sort of a chop it up, add it up sort of an argument. And let's see here. So we can talk about, what's going on in that. Why am I in that mode? That's weird. We can talk about what's going on in that little piece right there. We have a perfectly reasonable formula for how to compute flux through that piece, because that little piece is basically flat. And it's so small, the vector field doesn't really have time to actually change very much. So this is just the formula from the previous page, no problem. And again, chop it up, add it up, means I'm going to take that thing that I know how to do on the little piece, and then I'm going to add up over the entire surface. We've got to figure out how to actually do that, right, in practice. How do we achieve, right? But in the abstract, you're going to compute on individual pieces. We're going to add them all up. Everybody on board? Okay. All right. So good news. We already have a lot of tools developed for doing computations on surfaces. So you'll recall not long ago we entertained the question of how to compute the surface area, right, of a surface, and in general how to do a scalar surface integral. And the big idea was to say, well, chop it up, add it up, sure, but that summation is hard. But if I parameterize it, then I can talk about our old idea of pulling back through the parameterization, and the adding up that I want to do on that surface turns into, I just have to add up over that surface, and I love adding up over rectangles. World's easiest double integrals, nothing to it, fully armed, we know how to do that. Right? Everybody happy? So the big trick, parameterize, pull back through the parameterization, and again, a bunch of details we've already developed. So I'll remind you some of the players that were involved. We talked about the various partials of the parameterization. Those were tangent vectors. We took their cross product, and that gave us this thing called the capital N vector, which ended up being important. That's the vector whose magnitude is the area stretching factor and all that. And then we also, for kind of convenience purposes, we also needed to talk about the unit normal, like so. So these are objects that we've previously discussed, again, on what I like to call the large scale. But now there's also what I like to call the differential scale. So in other words, in the teeny tinies, right? As we're looking at an individual little piece, and here's one, there's an actual little individual piece of area there. Right? And the whole idea was its edge vectors that we calculated. The edge vectors were xu/du and xv/dv. Those are the things we actually crossed in order to compute the area there, ds. This ds, we ended up with this formula. This is all flashbacks to a couple days ago. Is everybody good? Okay. So what I'm going to do now, and I'm going to pull this out of nowhere for the moment, but I'm going to argue that these two products here are the same. And I know they don't look it. They look to be different formulas involving different things. I claim that they're the same. And here's how you can best see it, or here's my favorite way to see it. Both of these things that I claim are equal can be pretty easily observed to equal to little n times the magnitude of capital N times du/dv. Now, how could both of these things be equal to that? Well, First of all, notice that this product right here, little n times the magnitude of capital N, what can we say about that? Well, that product points in the direction that little n points, which is also the same direction that capital N points. Let me say that over again. This product points in the direction that capital N points, and its magnitude is the same as the magnitude of capital N. So this has the same direction as capital N, it has the same magnitude as capital N. It looks like a duck and quacks like a duck. It's a duck. Right, and then of course, obviously, du dv comes along for the ride. Yeah, everybody good? Okay, but then also, kind of conveniently, I can observe that, if I can get the thing, okay, there we go. That is ds, old news. And then, of course, obviously, little n is little n. So these two things that I wrote down are equal to each other because they're both equal to the same thing. And again, that's this little mathematical bank shot that it comes up a lot in math. It's a really good little method to keep in mind. You don't have to pick A and try to work towards B. You can just start with C and connect C. Whoops. I had the wrong button there. Connect C to each of A and B. Nice technique. Okay, so that said, what am I going to do with the fact that these two things are equal to each other, and who cares that these two things are equal to each other? What I'm going to do is I'm going to take those two formulas, I'm going to give them a name. I'm going to call this the ds vector. And this ds vector has two really nice features. Let's see here. Its magnitude. What's the magnitude of the ds vector? Well, if you look from this point of view over here on the right, I see a unit vector being multiplied by ds scalar. So this ds vector, its magnitude is the size, namely the area of the piece of surface in question. Now, what can I say about its direction? What direction does this vector point? Well, this vector points in the direction that is perpendicular to the surface. And a vector perpendicular to the surface is how we describe an orientation. And so, reminder, if you have a piece of surface, if you look at my hand here, right, the way my hand is oriented is entirely described by, what direction is this vector perpendicular to my hand? If you know what direction the vector is pointing, then that tells you how my hand has to be, this little piece of area that is my hand has to be arranged. Is that cool? Everybody good? Okay. All right. So, pretty neat thing. This ds vector, this one thing, tells you everything you need to know about that little piece of surface. You want to know how it's oriented? Cool. You want to know how big it is? Bam. It's all encoded in this one thing, the ds vector. So that's why this ds vector is interesting, and why we are going to give it this name and introduce it into the system. Okay. All right. And we are ready to do business now, believe it or not. Here we go. You want to compute the total flux. Recall, we argued previously that the total flux is the sum of all these individual little pieces of flux. Recall also, on any little piece, we derived this formula, F dot n times ds. This is the perpendicular velocity times the area. Easy motivation for how much flux is going through a tiny little piece of surface. And then I notice, check it out, little n ds scalar is our definition of the ds vector. So this is an alternative way to write the flux. Let's see here. Let me erase. I got a bunch of junk going on here. Alternative way to write flux. You can write it as f dot nds, integral f dot nds. You can also write it as integral of f dot ds, which is very compact and convenient. Very nice. And now, of course, we have this alternative formula for ds, that it's capital N du dv, and that gives us yet another formula for how we can write flux, f dot capital N du dv. So, a bunch of different formulas. They all have their different merits. Let's see here, and again, let me try to clear up the mess here. This first formula, whoops, I hit the wrong button. Let's try that again. This first formula, this is how we motivated the idea of flux in the first place. So that's, of course, a really natural, really important formula to be comfortable with. This is what connects flux to applications, right? So that's a valuable thing. Let's see here. The second formula, this formula right here, it requires the fewest pencil strokes, which I think has got to be worth something, right? But it also is what I'm going to call really the most natural of these formulas, in the sense that I see here the vector field. That's what, comes to me in the statement of the question as, this is the vector field I want to compute the flux of. And then I can see separately, completely independent of that, this ds vector, which is telling me nothing about the vector field itself, but everything about the piece of surface that I'm relating to the vector field. So this little sort of, drawing it like that with the everything on the left is vector field only and independent of the surface. Everything on the right is surface only, independent of the vector field. And mathematically, that's actually pretty natural then, because it keeps the ideas sort of separated. So, all right, and then of course, obviously, we're going to be fans of this formula right here, because this is something I know how to compute. I know how to compute double integrals. I know how to compute capital N vectors. I know how to do dot products. Right? We know how to do everything. This is what we call pulling back through the parameterization. This is your plug and chug, turn the crank formula, which of course, we're going to need to be able to do. Okay, how are we doing? Is everybody happy? Okay. All right, now there is a sticky issue that I need to talk about before we actually dive in and get our hands dirty. I point out that when you parameterize, when you parameterize, the parameterization is always arbitrary. We just parameterize whatever way is the most convenient, and there's a bazillion ways to do it. And yet, that parameterization gives rise to your capital N vector. That capital N vector gives rise to your unit normal vector, which describes your orientation. Oh, wait a second here, though. When you are asked to compute a flux through a surface, they're going to indicate which way they call the positive direction through the surface. Right? There's a big difference between, let me try to think of a good metaphor. If I have a region of space and I'm counting mosquitoes flowing into my region, that's a bad thing. Mosquitoes flowing out of my region is a good thing. That distinction between in versus out matters, right? So let's summarize again. This is arbitrary, but this is critical, and that's a bad combination, right? So we're going to have to figure out how to address that, and I'm going to make a quick analogy here before we go on. I want to remind you, when we do vector line integrals, we parameterize. The parameterization gives us a velocity vector. The velocity gives us our unit tangent vector, namely our orientation. Right? So now just think about it. If you've been asked to compute, again, going back to the vector line integrals situation, if you've been asked to compute, the amount of work that it takes to drive a certain mountain road, well, you have to drive the correct direction. If you go the wrong direction, you're going to compute the exact negative. Right? Drive the mountain road, whoa. You talking uphill or downhill? Right? Because uphill burns a lot of gas. Uphill drains your battery if you have a electric or hybrid, right? Going uphill drains your battery. Going downhill charges your battery. Did y'all know that one, by the way? It's a cool fact. Sometimes a lot of students don't realize this, but brakes, the way brakes used to work, well, and still work in most cars, is friction. And that turns the kinetic energy of the car into heat and into breaking down the chemical bonds that hold the brake pad together, etc. Right? So it turns kinetic energy into useless, wasted energy. Okay, electric cars have something called electronic braking, and it sounds like some of y'all are aware of this. It turns out that if you're clever with the arrangements of magnets and coils of wire and how you hook it up to the battery, you can turn the kinetic energy of the car into battery charge. And it's a very clever construction. It's a neat little engineering / physics arrangement. It's very cool. So in next time you take an E&M class or some sort of a related engineering class, you might actually see how that works. And it's not that big a deal, but it does use some subtle physics ideas and some very clever arrangements of engineering. So the kinetic energy gets turned into battery charge, and that means that there's less kinetic energy in the car. In other words, it slows down the car, and thus the term braking. If you're going downhill, you can just ride the brake. Gravity will keep you going. You ride that brake, rather than getting more and more kinetic energy, you're just getting more and more battery charge. So, pretty neat phenomenon. So, anyway, point is, it really matters. If you're interested in computing a line integral, whether you're going the correct direction or not matters to the tune of a minus sign on your answer. And totally analogous, if you're computing a vector surface integral, it matters that your orientation be correct to the tune of a minus sign. And if you parameterize backwards, you're going to get a wrong answer by a minus sign. Okay, now I want to plant that thought there, and then we're going to worry about that in a minute. Let's get our hands dirty and actually compute a flux here. So we're going to start off with, fluid flow, as previously noted. We've got a vector field giving the velocity of the fluid. We've got a surface described here. It's the part of this paraboloid sitting over the unit disk, and then there's some discussion of its orientation being downward. Again, we'll come back and talk about that in a second. As you might expect, the question here is to compute the flux. And before we do anything, flux, here's our formulas for flux, and we're going to be focusing on this one right here. We're going to parameterize, we're going to pull back through the parameterization, plug and chug, just like we got through talking about. Okay. All right, so here we go. Let's parameterize. I am looking at a graph. Right, you can see right there, this is a graph. If you want to parameterize a graph, we use the graph parameterization. Handy dandy. Now, real quick, I want to insert what gives me the right to pick this particular parameterization. This is arbitrary. It's very convenient, but it's arbitrary. I made that up. There's a bazillion other parameterizations. Maybe one of those other parameterizations is the one I ought to be doing. Maybe this one's right. Maybe this one's wrong. I don't know. I made this up. Does everybody see the concern there, right? I mean, so we're going to have to worry about that for a minute. But that said, having gotten a parameterization, I can take the partials. I can then take the cross product. There's our capital N vector. Yeah, everybody good? Now, per the previous page, where I left a big mess that I need to clean up real quick. Per this previous page, again, come on, erase. I made up an arbitrary parameterization, and I have computed a capital N, which dictates an orientation, because capital N is pointing in a particular direction. And now is the time when I can actually see if I parameterized right or if I parameterized wrong. Because I can look straight at this vector here, this capital N vector. That vector is pointing in a particular direction. It's either right or it's wrong. And now I can just look and see. And again, I want to clean up my mess. That vector, let's see here. Where's my... Did I draw down here? No, I didn't. Okay, I need to zoom out. This vector, capital N, let me draw what that looks like. I'm going to draw it at, let's say, a point about right there on the graph. This capital N vector, there's an arrow for every point on the graph, but I'm just going to look at one. And which way does it point? Well, a couple of different ways you can think about this. This suggests that it points back toward the z-axis. This suggests that it points up, not down. That means it's going to be kind of like this, right? I know it's got to be perpendicular to the surface, so I know it's either that or this, one or the other. And given that it is, again, pointing back toward the z-axis and somewhat slightly upward, I claim that it's this orange one right there. That's the capital N vector that we produced. Is everybody happy? Okay, now, so to the question, right or wrong? Is this the way it's supposed to be? No, it's not. And it says so right here. The surface that I'm interested in, the surface that they asked me about, is oriented downward. That's the orientation I was supposed to use. That's what's supposed to be the direction through this surface that I consider the positive. That's what I was supposed to get for my N vector, and I didn't. I got the opposite one. So I parameterized backwards. I parameterized upside down, you might say. Everybody see that? Yeah.
Why are we not looking at F? So F was...
Oh, we'll get there. We'll get there. Yeah. No, right now we're interested in the surface, and the vector field will make an appearance in just a few minutes. Yeah.
Can you remind me of oriented downward means again?
Yeah. So oriented downward means, so when you look at any surface, let's see here. Let me come to this picture right here, and let me erase my junk here. And we'll talk about, again, at a point, let's say right there. There are two possible what we call orientations on the surface. Orientation is an indication of which way through the surface we're talking about, which way perpendicular to the surface are we talking about. So this, what I'm drawing here in green, is an orientation in the sense that this is one of the directions perpendicular through the surface that you could move through the surface. But there's this other option, which is, well, I could, I suppose, move perpendicular through the surface kind of this way. It's a little bit uglier to write, but there's that blue direction, right? So give me 2 seconds. Trying to keep track of fluid flowing through the surface, well, are you talking about, is the positive direction the green one or the blue one, right? And so now how you describe these things is a little bit awkward. It's a little bit bogus for me to say, well, the green orientation is downward, because it's not pointing straight down, right? But you will notice that the green orientation vectors are all pointing at least somewhat downward, and the blue vectors, none of them are pointing in any sense downward, right? So it's a little bit sloppy language, but if I say downward, which one do you think I'm talking about? I'm probably talking about the green one, right? So we're sloppy with the language unavoidably because, describing the distinction between these two things in words with precision is implausible. So, sloppy language. Does that make sense?
Yeah.
Okay, yeah, you had a question.
So the orientation just refers to the normal vectors to the surface?
Yeah, that's right. Exactly. So when we talk about an orientation, we're talking about which of the two possible directions through the surface is the positive direction. Yeah.
So if you had a plane parallel to the z-axis as your surface,
oh yeah, then you can't talk about upward and downward. That's right. So if your plane is vertical, then again, you got to get creative with the language and figure out what is the exact word that distinguishes the one direction from the other direction. And if it was like let's say your plane is the XZ plane, then I guess I would talk about one of the orientations being in the positive Y direction and the other one being in the negative Y direction, for example. Does that make sense?
Yeah.
Is everybody happy with? So if you have a sphere, you can't say upward or downward. That just doesn't work. And you can't say positive Y and negative Y. That doesn't work, but you can say inward and outward. Right? No. Okay. All right. So yeah, orientation's a little bit hard to talk about, but those are the options. Okay, so bad news. We parameterized wrong. This parameterization goes the wrong way, whatever that means. It's hard to visualize. By the way, it's a lot easier to visualize when you're talking about curves. If you parameterize a curve, you can just kind of see which direction it goes, because you can just be like, all right, as time increases, which way am I going, right? It just kind of leaps off the page at you if your parametric curve is right or wrong. And it just doesn't with a parametric surface. The fact that this is upside down, really not obvious at a glance. So what you have to do, I wish there were an easier way around this, what you have to do is take your parameterization, cross those fingers, right, hope for the best, and then look and see with your normal vector. And compare that to what you were supposed to do in the statement of the question. Okay. All right, so we parameterized wrong. What are we going to do? We're going to have to start all over? Or for crying out loud, we have to start all over? With a different parameterization. What other parameterization would I even pick? This is clearly the easiest parameterization. I don't want to find a whole new parameterization and have to start over. The good news, we talked about this previously, if you parameterize backwards, like we did here, you're just off by a minus sign. Your normal vectors are pointing not just the wrong direction, they're pointing exactly, perfectly wrong direction. And perfectly wrong means only off by a minus sign, right? So all you have to do, if you find yourself in this situation where you've parameterized the wrong way, just insert a minus sign. And you're good. Yes?
Will that always be the case? If we parameterize the wrong way?
Yep.
It's always off by it?
Always off by exactly a minus sign. And look, you should also annotate. You should, always explain your reasoning. And so, you would want to write something on the side here by. I wrote a lot of words here. You don't have to write, all that, but you can say in wrong, frowny face, point, good, full credit, you're good. Right? You just have to recognize that you parameter. You have to be right about it, right? But just recognize that you parameterized the wrong way, and arrow to your minus sign, and go about your calculation. Yeah. Okay. All right. Okay. So, I can get this done. Yeah. So fine. Let's see, now here's where we're going to plug in. Our vector field is going to make an appearance now. Reminder, our vector field is x, comma, y, comma, minus 1. So I'm going to write down x, comma, y, comma, minus 1. Wait a minute, I need it in terms of u and v. How do I write x, comma, y, comma, minus 1? Well, parameterization tells me how to plug in. X and y are u and v. Right, so x, comma, y, comma, minus 1 becomes u, comma, v, comma, minus 1. So that's just pulling back through the parameterization, plugging in other words. Don't forget, you also have to plug in for your normal vector n, which again, formula on the previous page. Right, there's your normal vector n. You plug that in, and dot it up, and lo and behold, you have yourselves a double integral. And we know how to compute double integrals. I've advised polar coordinates in the UV plane because we're going around. This is a unit disk per the statement of the question. This is very polar friendly right there. This barely screams polar coordinates. That'd be my advice on computing this. Is that cool? Okay. All right. Okay, let's see here. Let's go through one quick example here, and then we'll call it a day. Sometimes you get lucky. Y'all know I'm all about the getting lucky, the geometric good fortune, and little shortcuts and hacks. Mathematicians are, in some sense, lazy, and we want to avoid effort whenever possible. Right? As we should be. And so this is one of those examples. Sometimes there's a real big effort saver, and you want to capitalize when you can. Okay, so we've got this plane y equals 3 right here, and our surface is the part of that satisfies a certain weird inequality. And so, okay, all right, so it means our surface is something vaguely like that, but I look at these fourth powers up here, and I'm a little concerned about how do I deal with the fact that those are fourth powers, but we'll get to that in a few. So we want to compute a flux, and here's the first little bit of good fortune. Notice every point that I'm interested in my surface, they're all in that plane, y equals 3. That means that for my entire calculation, y equals 3. And if you plug in y equals 3 into there, you get 0. And that means that our vector field has a 0 right there. So that's my first observation. Everybody see what happened there? This is a big geometric good fortune. The mere fact that my surface is in a certain plane allows me to rewrite my algebra for my vector field. Everybody happy? Okay. All right. Now here's the other, related bit of good fortune, and that is that if I were to look at my normal vector here. Oh, by the way, notice positive y direction, and thus my normal vector is like this. Well, I know exactly what the unit vector is in that direction. My unit vector, my little n, is 0, 1, 0, because it's clearly pointing in the positive y direction. There is only one unit vector pointing in the positive y direction. And that means that my ds vector has zeros there and there. So there and there. So when I'm looking at f.ds, there's f and there's ds, and that dot product's clearly 0, and again, walk away. I didn't have to parameterize. I didn't have to deal with a resulting double integral. Sometimes you get big time lucky, and when you do, capitalize on it. And this is a great place to draw the line. And we'll see y'all tomorrow. Yeah, see you tomorrow.